I'm going to be presenting on establishing convergence threshold for pre-trajectory sampling with batched execution across random quantum circuits. That's a mouthful, I know. Okay, so let me give you a little bit of motivation as to why we need better simulation methods. So first of all, when we're trying to simulate a noisy quantum circuit, it takes a lot of computation. It's computationally expensive. So when we're trying to simulate a pure quantum state, something that has absolutely no error applied to it, we need 2 to the n numbers where n is the amount of qubits. So in a situation where we could have 20 qubits, that would be about 1 million numbers or 8 megabytes of memory. That might sound like a lot, and it kind of is, but it's super manageable. The problem is that real life systems do have noise, and in order to accommodate for this, we need to use a density matrix with 2 to the n rows by 2 to the n columns, or 2 to the 2n numbers. When we go back to our 20 qubit scenario, that's over 1 trillion numbers or 9 tetrabytes of memory, which is super unscalable. One of the solutions to this is the trajectory simulation method, which uses M Monte Carlo samples, where each trajectory will track 1 2 to the n pure quantum state. It will randomly sample which errors occur, and then it will collect the output. Averaging across all of these trajectories, you will eventually recover the density matrix result. The problem, or not necessarily the problem, but a key point about these samples is that they can be far less than 2 to the n. In our example where we're using 1 million numbers or 20 qubits, we can set m to be 10,000, which only has a 1% accuracy deviation while using 1 million samples or 1 million numbers instead of 1 trillion, which is huge. The problem with these trajectory simulations is that they have a couple of limitations. First of all, you can only take 1 shot per trajectory, you have to do random sampling, and you're not able to collect any information on which errors occurred. PTSBE, the pre-trajectory sampling big thing, actually fixes this. So it allows, by pre-sampling the noise trajectory, we can take multiple shots per 1 state preparation, we can do more strategic sampling, and we can actually get error metadata back. So how does PTSBE actually work? So first, we start with a noisy quantum system where errors can occur during its execution. Then we pass it into the sampling algorithm that will pre-generate specific error patterns depending on what we're going for. This could be most likely errors, a specific kind of error we're trying to measure. This could also be targeting specific qubits. Then we get these things back called Krauss operator sets. You don't have to worry about the name for right now, but essentially what these do is they specify which errors happened and where. Each set, like K alpha and K beta, is one possible complete error scenario that's running through the circuit. Then we allocate measurement shots for each of these scenarios. Let's say we have an error pattern that has a 90% chance of happening. That means that we're going to give it 90% of our shots. The more rare that one of these error patterns are, the less shots that we're going to give it. So then we run it through these accelerated simulators using GPUs. The key here is that we are preparing one state per error pattern. And then we measure it many, many, many times, whereas the regular trajectory would do it every single time, which is really computationally expensive. And then our output is this massive set of simulated noisy data. Okay, so here is how PTSBE performs on a 35 qubit system using something called Q to Q. This is how our sampling algorithm is scaling. So we're first going to pay our attention to this green line here. Notice how it is kind of climbing up. When we start down here, we are starting with 10 shots per second. But as we increase to around 10 million shots, we're starting to take 1 million shots per second, which is I think it's an order of 5 magnitude increasing. So why does it work this way? Well, preparing a quantum state, as I've said, is computationally expensive, and that's because this is where all of the qubit gates are. So, but the difference here is that when we're taking these measurements, they're actually very cheap. So as I've said before, PTSBE will prepare one of these states, and then it will measure many, many, many times. But the point here is that the more that we measure, for one prepared state, the more we can kind of spread out this expense of this like setup cost. And all this time, it's going to be climbing up in speed. Now, if we look at the blue line, this is the proportion of the unique shots of the system. So what this is essentially saying is, if you look right here, it has 100% at, or 1.0, at really, really high shot counts. What this means is that almost every single measurement is providing a unique and a really distinct outcome. A really key thing here is that we're not, what's the word, saturating. We're not saturating the probability space, but instead we are really covering it very efficiently. So one of the keys here that we're seeing is that we are seeing a really improved speed up time while also getting really valuable information from every single shot. Okay, so in order to run PTSBE at scale, I created an automatic research infrastructure using Apache Airflow, which is an API. Here is our little workflow down here. So we start with circuit generation. This API will create these random quantum circuits from parameters that we get to specify. That could be something like the certain a depth of gates. This could be the amount of qubits that we're deciding, and this could also be the certain gate sets that we want to look at. And then we look at job scheduling. Job scheduling is where the system will kind of schedule a job automatically, and then it will submit it to this GPU cluster. This way, we don't have to do anything, we don't have to launch anything manually, but instead, the Airflow will orchestrate everything itself. Then we are looking at CUDA-Q execution. This is where all of our programs get to run on nodes using MPI parallelization, and essentially we get to use many GPUs simultaneously to run our program. Finally, we have data aggregation. This collects all of our simulation data and our convergence results and then puts them into analysis. So the really big key here is that this is automated. This means that we can run hundreds of different simulation experiments, we can sweep through all sorts of different parameters, and we get all of this data without having to manually intervene. So what this means is that we can more systematically see like how PTSBE converges, and yeah, exactly what I said. Okay, so let's now look at how PTSBE actually converges in comparison to the standard trajectory sampling, which is the traditional method. So the point here is that we generated 10 random quantum circuits using our code, and then we took 3 different metrics to compare them. The baseline here is the density matrix. As I said earlier, it's the most exact. The only problem with it is that it can only handle smaller systems, so we are using 7 qubits in this instance. So what this graph is essentially saying is that our accuracy measurements is dependent on the total variation distance to the density matrix. So essentially what this just means is that the lower that this bar is, the closer it is to the exact answer. PTSBE, our method, is in blue, and then STS, the traditional method, is in orange. As you can see, PTSBE is experiencing a significantly lower error rate, and then it also has a 35.6% better accuracy than STS does. Both of these methods are converging to density matrix, but the PTSBE is doing it much faster. So if we look down here, here are our key findings. We see that PTSBE is winning on 10 of the circuits, which is huge. What we also see is the sample efficiency of 0.01 times means that we are using 1% of the trajectory runs that STS usually does. This means that we are getting better, more accurate results with 100 times less trajectories and circuit runs using this batch method. So essentially what this is doing is this is confirming that PTSBE, its approach with using pre-sampling and batched execution results in much more efficient running than STS does, and then it also provides far more accurate results. The end.